everyone, welcome back to HackCode. Today we are diving into a classic coding problem that is frequently asked in technical interviews. LeetCode 33. So search in rotated sorted array. This challenge examines your skills in working with rotated arrays and efficiently using the binary search. While it may appear tricky at first, fear not. By the end of the video, you'll grasp how to locate an element in the rotated sorted array. So let's jump in and conquer this problem together. So here, this is the question: search in the rotated sorted array. So there is an integer array nums which is sorted in ascending order. Remember, there is no duplicate. It's all a distinct values. So prior to being passed to the function, the nums is probably rotated at an unknown pivot index. That is k. Basically, k lies in the range of 1 to n minus 1, where n is the length of array, such that the resulting array would result in nums of k and nums of k plus 1 all the way to n minus 1, and then the starting k minus 1 elements. So for example, this is a given array. This might be rotated at pivot index 3, so that is here, and we'll get all this 4, 5, 6, 7 to the initial part of the array and followed by these 3. So that's how it rotated. So given array nums, after the possible rotation and integer target, so we have to return the index of the target if it is in the nums, or else like we have to return -1 if it is not there in the nums. Simple. So you must write an algorithm with O of n runtime complexity. So O of n runtime complexity is always like it's like dividing the search space in each iteration, right? We had to cut down the search space in each iteration. So that actually talks about binary search. So if it is not O of log n, we might think linear search, right? We can just iterate over the array and then return the index if we found else -1. So yeah, that's the crux of the question, O of log n. Key point. So here they gave the examples, right? Here the target is 0, we have written the index 4. So here the target is 3, but 3 doesn't exist in the array, so we return -1. So same with here, it doesn't exist in the array, so we return -1. So here the constraints, array length would be less than 5000. So basically it contains maximum is length is 5000 elements in that array. So each element range lies from the -10 power 4 to 10 power 4. Same with the target. So nums is in ascending array, that is probably rotated. It's always be rotated because k is 1, right? 1 to n minus 1. If they said k is 0, we can assume that there will be points where k is like array is not rotated. It's just a sorted array. So let's dive into the approach. So approach is just a modified binary search here. So the key intuition behind this approach is the observation that even though the array is rotated, at least one half of it must be sorted at any given point. So let's look into the situation here. We have this array, right? It's what they gave us an example. So here it's initially sorted and it is rotated at the third index. So we get all this like from 3, 4, 5, 6 would come first, all the indexes, so followed by 0 to k minus 1. So at this any given point, like we got this like 2 sorted arrays, right? This is how we should constrain our search space too. So we generally start with left and right pointers for this binary search, and then at each step we find the middle of the element of the current range. So we check if the middle of the element is equal to target. It's a happy pass scenario. If middle is equal to target, then we return it. We did it in the index of this element. If the left half of the current range is sorted, then we check if the target lies in the half by comparing it with the nums of left and mid. So if it does, we adjust the right pointer accordingly. So otherwise we adjust the left pointer. So if the right half of the current range is sorted, that is nums of mid less than nums of right, we check if the target lies in that half by comparing it with the nums of mid and nums of right. So if it does, we adjust the left pointer accordingly. Otherwise we adjust the right pointer. So we need to repeat the steps until we get the left pointer exceeds right pointer. So that's not a valid search space, right? We have to return -1 because we exhausted all the search space and we didn't find the target, so it's -1. So by exploiting the property of at least one half of this array is being sorted, we can perform a binary search efficiently, and that's allowing us to find the target in of log n time complexity, where n is the number of elements in the array. So this is the coding solution we have. So let's go to the solution, right? So we generally initialize all the variables first. So left is initialized to 0 here, right to n minus 1. So this is the tuple unpacking assignment basically. Here we iterate out the loop until left is less than or equal to right. So first step is to find the mid element. So that is done using left plus right integer division by 2, because let's say the for even length array it's quite simple, right? Even length we get only integer. If it's odd length like 7, we get 3.5. So 3.5 index is not valid, right? For that case we have to take only 3. So that's where this integer division comes in. So by this for double slashes indicate it's an integer division. So when it is 3.5, the result would be flowed to 3. So the first check, right? Here nums of mid is equal to target. Then we return the mid, that is the index. So it's a happy path scenario. And then we have to check if the left side is sorted. Basically, in this, if left side is sorted, if we have to check if the target is within the sorted left side. So first check is that one only. So this is just checking if this lies in this range. Basically, nums of left is just a plain English. We translate to code. Nums of left less than or equal to target, less than or equal to mid. If as we should not explore the right side. So we should say start exploring only left side. That means that we have to get the right index to the mid minus 1. So now we find a new mid and then we explore this left side of the sorted array. Else other part is like we have to explore the right side of the sorted array. For that we have to keep mid plus 1. Then we explore the left is equal to mid plus 1. Then we explore the new mid and new with this left plus right by 2 calculation. So the flip side is we have to check if the right side is sorted. So if the and then in that first check is we check if the target is within the sorted right side. So if S, we should explore only sorted right side, right? So that's why we are doing the left is equal to mid plus 1. Else the other part is like we should not explore the right side if the target is not in that range. So we shift right to mid minus 1 and find a new mid and explore between these ranges. So we do all these things. We come out of the loop when left greater than right, and then we return minus 1 when there is no element found in the given array. So if the element is found, we've just written the index here mid. That's how the oral code works here. So let's go to the time complexity breakdown. So here the time complexity, as we know, it's overflogging. Why overflogging? Because the algorithm divides the search space in half at each step by using the binary search. Starting with the entire array, it repeatedly narrows down the search space by comparing the middle element with the array's boundaries. So the division continues until the smallest element is found. I mean, not smallest element here, until the search, until the target is found. So because the search space is halved at each step, the time complexity is logarithmic, making it overflogging, where n is the number of elements in the input array. So the space complexity is constant because algorithm uses a fixed amount of extra space regardless of the input size. So it allocates only the few variables which are left, right and mid, and doesn't use any data structures that go with the size of the input array. So there might be cases where you use the data structures that grow the size of the input array, but that's not the case here. So this always makes the space complexity to be constant, which we represent using O of 1. So now execution. So I have got the code ready here. Let's try compiling this first. Yeah, it is compile and accepted solution too for all the 3 test cases passed. Let's try submitting this. So yeah, our solution beats 88.05% of the Python users. That's best solution actually, one of the. So on the memory also, it beats 31.41 of the users with Python solution. So yeah, let's go over the conclusion. So conclusion is, the moment we see overflogging, we need to think of narrowing down the search space. So indirectly we should be referring to the binary search. It should be some modification of the binary search. That's the main takeaway. So thanks for tuning into this episode of Hack Code. If you found this video helpful, be sure to give it a thumbs up and subscribe to the channel for more coding tutorials and talk concepts. If you have any questions or suggestions for future topics, feel free to leave them in the comment section. And until next time, happy coding.